All right, so let's begin with a word of prayer. Dear Heavenly Father, we thank you for this morning. Again, I thank you for these students. I just pray that you'd be with us today. Again, Lord, I just pray that you'd help us to glorify you in what we do, Lord. In your name I pray. Amen. So please turn in your homework. All right, so let me just, I'm going to just go back and recollect what I did last time real briefly. Basically what we showed was that if you look at the rational function 8x cubed minus 57x squared plus 94x minus 41, all divided by x minus 4 times x minus 3 times x squared minus 2x plus 5, then you can do partial fractions to rip it apart into a sum of basic rational functions. In particular, we have, I'm just going to write it in a slightly different format than I did last time. 8 plus 6 times x minus 1 over x minus 1 quantity squared plus 4 plus 7 over x minus 3 minus 5 over x minus 4. All right, so we worked that out last time. The example I want to start with today, continuing partial fractions, is to work out the partial fractions decomposition of what follows. So 3x squared minus 12x plus 21, all divided by x minus 2 quantity cubed. All right, so I want to find the partial fractions decomposition for something like this. First of all, it's a proper rational function, all right? So I don't need to do long division. I can just go looking for some undetermined coefficients, in particular a, b, and c, where we have a over x minus 2 plus b over x minus 2 quantity squared plus c over x minus 2 quantity cubed. You can say, well, how do you know it's that? Well, I mean, the best answer I have to you at this point in your education is because it works. Later, you can derive these things from more general abstract algebraic principles, but, you know, at some point here, you could, on the other hand, just to see that it's necessary, you could just take different values for a, b, and c and make a common denominator, and what you'd find is that you get some rational function that looks like the left-hand side. All right? So we do need all three terms, and we don't need anything in the numerator. All right. So the same song and dance as last time. First of all, multiply both sides by the denominator. All right? So that gives me 3x squared minus 12x plus 21 is equal to what? Let's see here. A times x minus 2 quantity squared plus b times x minus 2 plus c. Are you guys with me? I hope. I'm going to call that thing Pac-Man. So what happens if Pac-Man eats 2? So we get 3 times 4 minus 12 times 2 plus 21 is equal to, so 0, 0, and what's that? C. Yeah, wasn't so bad, was it? Let's see here. So this is 12 plus 21, which is 33. 33 minus 24 is 9. So C is 9. And then, for this kind of problem where you have a repeated root, of course we can't use 2 again, we've already used it up, right? But there's a simple thing you can do for this kind of problem that makes the partial fractions go really nice. this equation, Pac-Man, right? Pac-Man holds for all x, right? So you had a polynomial equation that holds for all x. What can you do to such an equation? Well, we had calculus 1. We can differentiate, right? We can differentiate Pac-Man. If we differentiate Pac-Man, what's that get us? What's Pac-Man prime? D Pac-Man. See, so I get what? 6x minus 12 is equal to what? 2a times x minus 2 plus b. See, it pays off here to not FOIL that out, right? It pays off to leave it in that format so you can let Pac-Man prime do its work. Pac-Man prime eats a 2. What's he get? 6 times 2 minus 12 is equal to what? B, right? Plug in 2 into this. What's b then? B is 0. I think you see where I'm going with this. What happens if we look at Pac-Man prime prime? What's that? Six equals what? Differentiating, we get what? Just 2a, right? So therefore a is equal to 3. And there you have it. So this is a nice trick to know about when you have a repeated root. You can differentiate the equation and plug in the root, and you get nice, simple algebra to work out. Let's see here. So what we found is that this is in fact equal to 3 over x minus 2 plus 0. I wouldn't usually write this, over x minus 2 squared. And then finally plus 9 over x minus 2 quantity cubed. At this point, I will ask you the same question I asked the previous section, which is, who should I call? Ghostbusters? No, not relevant. No. The answer, of course, is Jenny. I will now point out to you. Annoyingly, last lecture he zoomed out. You can't see it. You can. Oh, it's. Man, I tell you, I wish I had told you guys to watch the last one and not done this today, but the video is kind of screwy from yesterday in the last section. So here it is. All right, now that I've gotten this silly example out of the way, let's do something that requires long division. Let's see here. How about? Oh, I haven't completed the thought. I mean, of course, you can integrate what's in the purple, right? If I call this whole thing, if I call this whole thing f of x, right? What's the integral of f of x? I mean, the point of this is we can integrate what's in the purple, whereas I can't really directly integrate what's in the black. This is just straight up 3 natural log the absolute value of x minus 2, right? Plus what? That's the minus 3 power, right? So I go minus 1 over 2, there's a 9, and then I have 1 over x minus 2 quantity squared plus a constant. And there you go. That's the integral of that rational function. Right? Don't forget, that's why we're doing partial fractions, is so that we can integrate. By the way, this technique also has important application in differential equations. In the study of signal analysis, there's something called the Laplace transformation technique. And so very important for electrical engineers, how you guys analyze systems, signals to a certain extent. And in the study of the Laplace transform technique, the same algebra comes up. So it's important to learn it right the first time. That way when you take differential equations later, you'll have an easier time of it. Just a thought. It has interesting application there. All right, independent of this integration. So another example. let's see here. How about this? Something like the integral of x to, let's see, x to the fourth divided by x squared plus 1 times, I don't know, x squared plus, oh, I better not do that. That's not enough fun. That's not enough fun. Let's do x minus 3. That should be sufficiently yucky to illustrate the idea. So this time, I can't just go on my merry way and do partial fractions because, well, I don't have a proper rational function just yet, right? So what I have to do is I have to say, okay, well, x to the fourth, right, over x squared plus 1 times x minus 3 is equal to what? Well, it's equal to some polynomial plus a proper rational function. Now, how do I find that polynomial? I gotta do long division. Now, I think it's probably helpful for me to multiply out the denominator here. Let's see here. So this is x, what, x cubed? What do we got? Minus 3x squared. Then what? Plus x, very good. Minus 3. All right. So just a reminder how you do that. So we're taking x to the fourth and we're dividing x cubed minus 3x squared plus x minus 3. And let's see here. How do I get x to the fourth from this divisor? I have to multiply it by what? X, right. And that gives me what? That gives me x to the fourth minus 3x cubed plus x squared minus 3x. I have to subtract that, of course. So I get what? I get 3x cubed minus x squared plus 3x. Same degree as the divisor, right? So I'm not done yet. How many of these can you fit into that? 3, right? So I do plus 3. Now that gives me 3x cubed minus 9x squared plus 3x minus 9. Again, I subtract, right? And let's see here. So that gives me 8x squared. Ah, cool. Cancels, huh? Interesting. Plus 9. At this point, the remainder has smaller degree than the divisor. That means I'm done. That's the remainder. Okay, so this is the remainder. And what this calculation means for us is simply that this can be simplified how? It can be simplified as x plus 3 plus 8x squared plus 9 over x squared plus 1. I'm going to factor it again over x minus 3. So at this point, we have rewritten this improper rational function as a proper rational function plus a polynomial. All right. So of course, this we can integrate, right? You've been able to integrate that for quite some time now, I hope. But the other side, we're going to use the partial fractions technique for, right? So this, we're going to suppose we've got something like what? A plus bx over x squared plus 1 plus c over x minus 3. It's up here. Yeah. So yeah, that one is going to there. That's the partial fractions decomposition. Are you asking why is it not ax plus b? Or?
No, it's just no one's like separating out like everything.
Well, this is a linear factor which is repeated. Algebraically, that's different than this x squared plus 1, which cannot be factored over the reals. Now, of course, we can make all of these differences wash away if we would be content to work over the complexes always. But generally speaking, students revolt when I try to do this. So I will behave and do some, I will keep it real. Okay, so. Sorry, that was awful. All right, 8x squared plus 9 over x squared plus 1 times x minus 3. Right, so how do we solve that? The usual thing, right? Multiply by the denominator and work it out. I'll do that over here. Let's see here. So we get ax plus b times x minus 3 plus c times x squared plus 1 equals to what? Yeah, 8x squared plus 9. So I'm multiplying star by denominator. I will call this Pac-Man. So what should we feed Pac-Man? I think the easiest thing to feed him is what? 3, yeah. See here, so we have 3a plus b. Oh, duh. Duh, 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 duh. Why am I writing that? Why am I writing things that are obviously 0? All right. Let's see here. So how about that? That is c times what? 9 plus 1, right? Is equal to 8 times 9 plus 9. You can go either way. So this is 10c. I mean, sometimes I'm going to write a plus bx. Sometimes I'm going to write ax plus b. I really cannot explain to you why I do one or the other at a given time. That is too hard a question for me. I really don't know. I guess the double-minded man is unstable in all his ways or something. I don't know. See here. This is, what do we got? This is 9 times 9, right? 81. Okay, so there you go. C is equal to 81 over 10. 1 down, 2 to go. So at this point, I think what I'm going to do is illustrate the technique of equating coefficients here. So I don't know. I mean, I guess well, fine, I'll do it. So this is what? This is ax squared minus 3ax, right, plus bx minus 3b plus what? Plus 81 over 10 times x squared plus 1 is equal to what? 8x squared plus 9. So at this point, I need to label this thing. I'll call it ghost. There we go. I don't know. Whatever. So ghost is a polynomial on both sides, right? So I can equate coefficients. So we can look at the coefficient of x squared. We can look at the coefficient of x. We could look at the constant term. What do you guys want to do? I think x squared is an easy thing to look at, right? So if we look at the coefficient of x squared, what do we have? We've got a. Where else do we get x squared? Plus what? Plus 81 over 10 equals to what? 8. Okay, so therefore a is equal to 8, or 80, minus 81 over 10, right? In other words, minus 1/10 is A. And then, I mean, what do you think is going to be easiest to figure out? Usually looking at the constant term is easier. Let's do that. So if we look at the constant term, the coefficient of 1 up here, what do we have? What are constant terms in the ghost expression? Let's see here. Not this one. Not that one. Not that one. That's got, see, x, x, x. Oh, no x, constant. 81, and this one times that, right? Constant. And then on the other side we have a 9. So what do I have? I have something interesting, right? Because I've got minus 3b. b is what I'm after. I don't know that yet. Minus 3b plus 81 over 10 equals to 9. Which, of course, we can solve for b, right? So b is equal to what? So 9 is 90 tenths, right? So therefore, minus 3b is equal to 9 tenths. Therefore, b is equal to minus 3 tenths. Let's see, let me check my work. 90 minus 81 is 9. And 9 over minus 3 is minus 3. The 10th rides along. And there you have it. So returning to the start of all this, what we really have is the integral of x plus 3. Any questions about the long division? We can do more if the question is about more. X plus 3. What was A? Minus 1/10. All right. And then B was what? Minus 3/10. I see I could have factored a 10th out there, huh? Oh well, too late. And then C was what? C was 81/10. I'm writing these expressions in a rather inelegant way to start with, just to. So that's what partial fractions got for us. It got us that we can rewrite this rational function as this very nice expression over there, which we can integrate. Yes, yes, sir.
Shouldn't it be negative 3/10 minus 1/10 x?
Did I?
Because over on the right you have ax plus b, so it should the negative density x.
Oh, that's what you guys were asking me about earlier. I'm sorry. That's a legitimate question. So I've changed the meaning of A and B. Let's see, the easiest way to fix this is to go back to here in your notes and just scratch this out and say B and A. Because then what I wrote over here is legit, right? But what I wrote here is still not right. Thank you very much. That's a very, very helpful comment. And sorry to the person who tried to tell me earlier and I was too stubborn to listen. That is, by the way, the cost of my indecision on whether it's ax plus b or a plus bx. If I toggle between these two worlds during a given example, it would create an error, as I illustrated. On purpose, of course. Let's see here. Okay, with that said, you can integrate, right? I mean, this is 1/2 x squared plus 3x minus 3/10 the inverse tangent of x minus 1/20 the natural log of the x squared plus 1 plus 81 over 10 the natural log of the absolute value of x minus 3 plus a constant. One of the reasons I really like your book is he does have some nice examples in there where these things end up with a trig substitution, you know, and he shows you how to go through it. Like the last example in the section on partial fractions actually has the case of a repeated quadratic where he needs a trig substitution to work it out. Oh, okay. Thought we were playing that game. Let's see here. I think Sprano's over there. Any questions? I make a u equals x squared plus 1 substitution to get the natural log. The 2 becomes because if u equals x squared plus 2, then dx is du over 2. That's where the 20th come from the u equals x squared substitution. The first term here is just a plain old inverse tangent integral, and the minus 3/10 can be pulled out. So, all right. So I've showed you the usual song and dance, the usual techniques for how to solve partial fractions examples. Let me just look at my notes for just a minute and see if we can't see if there's other things you can do. I mean, there are examples which just have intrinsic difficulty. If I can find it. Where'd you go? Oh, maybe I should. Sorry, I'll get with it here in a second. All right. Where did I put? Oh. Where's my laser? Did I leave the laser sitting back there somewhere? Oh, it should be. It more or less looks like a black pen. Thank you. Haha. Okay, so of course, I think I posted like a global PDF of the notes, but I also have these chapter PDFs, which are sometimes convenient. Of course, we're in chapter 9. I would advise, no, I don't want to save it. I want to open it. Fine. Whatever. All right. Integration by parts. That's so last week. Let's see here. All right. Integrals of trig functions. Been there, done that. Implicit substitutions. Still fresh. Let's see here. Partial fractions. All right. It's like here's another example of sorry. So here's another example of a long division. So if I wanted to integrate this thing, 2x cubed plus x squared plus 3x plus 5 divided by x plus 3, then this is the long division. So, to start with, I need a 2x squared in order to get 2x cubed, right? But then 2x squared gives me minus 2x squared and minus 6x squared, right? You add these, you get minus 5x squared. Then I need the minus 5x to match this. and so forth, we get the remainder of minus 49, which gives us that this fraction is actually this polynomial, 2x squared minus 5x plus 18, see? Minus 49 over x plus 3. And of course that we can integrate. So here's a slightly more exciting example of long division, right? What other technique could you use to do this one if you were so inclined? That technique that none of you really understand, but you have all been trained to do, like so many monkeys and so many typewriters? What's that? No. Hey. I don't view you guys as monkeys and typewriters. I'm talking about your high school math teachers and their incessant desire to teach you synthetic division. Synthetic division, like synthetic. Synthetic division only works for linear factors. So you could also do this with synthetic division. But if you wanted to ask me how to do it with synthetic division, I would have to tell you, no. I won't cover synthetic division, I refuse. Because long division does everything. And it's more general. Like long division, we can divide by a quadratic, a cubic, a quartic, whatever. Float your boat. It's totally general. Synthetic, meh. Here's another one. This one, you see 2x squared plus x squared plus 3x plus 5. I've got a cubic upstairs. I've got a quadratic downstairs. And I just do the long division. So long division gives you this. All right, I didn't include the details of that. But once you have that, of course, you can integrate this one just to get x squared minus 7x, right? And this piece, on the other hand, factors, that's x plus 1 times x plus 3. And so you do the partial fractions, out pops this, and you integrate, right? We've done an example like this before. I hope this is starting to look familiar. Maybe, maybe not. All right, still, really, we did examples like this already. Here's another one we kind of did. Here's a more awful example. If I had x to the 6th plus 2x cubed plus 2x plus 7 over x cubed plus 4x squared plus 3x, then I can do the long division and get 113x squared plus 116x. And that's my, my polynomial piece, as you can see right here. And then I just have to do partial fractions on this lovely equation. Ew. That's actually x times x squared plus 4x plus 3, so it actually is not too bad. You just need a, b, and c to deal with that. Yep.
On this last example, how did, like, can you explain how you got ax plus b as the numerator of the first part? You had, like, ax plus b over x squared minus 1.
Which example are you talking about? Are you talking about this one, or the one we did, the one I wrote on the board? How did I get this?
Yeah. How'd you get that over x squared plus 1?
That's the partial fractions decomposition. I mean, once I have, hypothetical, if I had 77 plus 13x squared over x squared plus 4x plus 5 times x squared plus 9, what would the partial fractions decomposition setup be? Well, this one, I can complete the square. This is x plus 2 quantity squared plus 1. So this, I use a times x plus 2 plus b, or as I said, I can't make up my mind whether I put this here or here, but whatever. And then I got plus cx plus d over x squared plus 9. That would be the partial fractions decomposition. If you're asking me why that's true, you're asking me to derive the general format for partial fractions decomposition, which means I would have to take arbitrary rational functions with arbitrary factorizations and prove that this works backwards. You really don't want me to do that. I don't think that's really your question either, though. That's the question we professors want to hear people ask, but it's not really the question you're asking, I don't think. And so, for example, you're really asking what else could happen, right? If I square, if this is squared, then I add a ex plus f over x squared plus 9 quantity squared.
I think I understand what happens in the denominator, but it's
The numerator, that's the thing, numerator does nothing. The partial fractions decomposition is almost completely governed by the denominator, with one little proviso. It can't be the case that the numerator has a greater degree than the denominator. If it does, we pay a heavy price. We have to do long division to simplify it to a polynomial plus a proper rational function. So part of the point of these examples in my notes is to kind of give you gory examples where that's happening. Yep.
Or like you said, like with the degree of the numerator, it has to be less than the degree of the denominator. But that top up there, we just did it to use like factor, like multiply those two polynomials
This one?
together when it'd be technically a x to the 4th power, making a higher power.
What did I?
That would be a problem with it.
Oh, okay. No, that's fine. I do the same every day. Let's see here. Here are the awful details for that problem. Actually find the fractions a and b are not so nice there. They end up being 0, 3/2. And I guess a and b are okay, but c is apparently 223 over 2. All right. Let's see here if I can't. I'm trying to find. So this example here, I think, is an example of something where 9.4.8 is an example of something that's maybe just a little bit, maybe it's a little bit too much for just trying to calculate by hand. Like at this point, I think, well, maybe you should use some technology. So this particular quartic factors by grouping to this and that, which gives you x squared plus 9 times x squared plus 4x plus 5. So it's the product of irreducible quadratics. Now what that means is I've got no nice zeros to plug into the expression. I'm almost forced to use like equating coefficients. So the partial fractions decomposition for this is that, right? Because this gives me the x squared plus 9 gives me this piece. The x squared plus 4x plus 5 gives me that piece. You notice here I'm being inconsistent with my insistence that I put x plus 2 here. So here I've fallen, I'm doing it like your book does. Your book doesn't put x plus 2, it just puts x when you have something like this, right? You could go either way, right? I put a times x plus 2 because I'm trying to make the integration that follows easier, but in principle you could also just put ax plus b here. It wouldn't be really different. This is a difference between my way of thinking and the book's way of thinking, is whether or not you put x plus 2 here or x when you're completing the square kind of thing. So again here, in this example, I'm actually in concert with the book. I didn't put x plus 2 there like I would usually lately. Anyway, then you multiply by the denominator, and you get this. You FOIL this stuff out, and you get that. There's nothing particularly nice about any of these equations if you look at the cube, the square, the linear term, or the constant terms. They're all coupled. Right? So how do you solve this kind of problem? I mean, you have 4 equations and 4 unknowns, if you look at it, from the different orders. 0 equals a plus c, 2 is equal to this, 3 is equal to that, minus 9 is equal to that. So how do you solve this? Well, you can solve by elimination and substitution, right? And so I do that, and I somehow find my way to the solution for what? Where do I get it? Where did I get? I got one of them. I figured out a from something in here somewhere. So, somehow, by some manner of chicanery, I figure out a has a value of what? I guess I didn't figure out a, but what I did was I eliminated a, and I got 3 equations, 3 unknowns, right? This is how you solve 4 equations and 4 unknowns. You try to eliminate one of the variables, you get down to 3 equations, 3 unknowns. Then you try to eliminate a variable there, and then you have 2 equations and 2 unknowns, and this is how we solve systems of equations, right? But really, once you've eliminated one of the variables, you got 3 equations and 3 unknowns. You can rewrite it as this matrix problem, and you can use something called Cramer's rule if you like to solve it, and there it is. But really, the best way to solve this is to go back to the original system of equations and write the so-called augmented coefficient matrix, do what's called row reduction on it, the reduced row echelon form of this matrix, this is a typo. This isn't supposed to be here. This operation on this matrix gives you all of this. And from this, I can immediately read A is equal to 3/5, B is equal to 27/20, C is equal to minus 3/5, and D is equal to minus 7/4. I would, of course, not ask this of you on a test, right? In fact, I don't think I've even given you a homework as insidious as this. Why am I telling you about it? I want you to understand that calculus and other math, I mean, we have this idea that math is compartmentalized, right? But what I'm showing you right here is matrix algebra. It's linear algebra. This is something you should have seen in high school, not the partial fractions of this complicated nature, but how to solve 3 equations or 4 equations and 4 unknowns, right? Now, maybe you did or didn't look at it in terms of matrix operations, but I want to tell you that because that's probably the most efficient way to solve these kinds of yucky equations is with technology like this. Or you could use Mathematica. Anyway, so I think that's all I got for you in terms of just standard partial fractions. I got tons of examples in the notes. I won't cover them all. I don't think there's anything else in here I need to talk about. I do have some nice sort of ugly, like here's an example where we have x squared plus 4 squared, and you actually have to work out this, and I do, and then you can integrate using trig substitution and so forth. But I'll let you guys look at the notes for the harder examples. I'm not going to do them in here unless there's a question, so I'm going to put this away for now. So, I mean, of course, the examples I've worked in class up to this point before I had the projector out are more the kind of thing I would tend to actually test you guys on in a time pressure situation, right? The kind of thing I just showed you, you need some time to work out, right? But it is within the realm of possibilities. You can calculate. Yeah, that's the point here, is with partial fractions, we can calculate the integral of any rational function. All right, so I'm going to move on. Unless there's a question about something. So what we have left this week, right? The next section is on rationalizing substitutions. So it's basically like taking the partial fractions idea and taking the implicit substitution idea and meshing them together to do a couple of interesting kinds of problems, all right? There's really about, as I see it at the moment, there's 3 main problem types that I've identified in that section. I'll try to show you one of each, all right? And then past that, we have numerical integration. Numerical integration is like completely different, all right? And I would say pretty easy, really not much to do there except learn a couple formulas and how to work with them. And that's what we have left to do this week. So the rest of the week, past that, of course, we'll have for your homework questions and review questions and so forth. So we should have plenty of time for you guys to ask questions about this week, all right? So maybe if you run out of questions, I'll come back and do some of those harder examples in the notes later this week, all right? I try to structure my courses this way. Like usually I'm a little bit hurried right after a test because I'm trying to create some space right before the test for you to kind of collect your ideas and draw things together before the test. And so that's why we have kind of a couple of days where we don't really have much going on this week. Right? Trying to give you time. Because we have a test when? Yeah, next Tuesday. That's right. So this is, I think, section 8.6. Although I was looking at a different edition of the book this morning, so I might have my numbering off. Let me check. No, 8.6 is right. All right, so a few examples I want to show you guys. Let me get to it. All right. Start with a relatively benign example. How would you integrate something like dx over 1 plus root x? So I would say, generally speaking, these are rationalizing substitutions. Rationalizing substitutions. That's the theme for this section. It's a substitution we can make which changes the given function into a rational function in a new variable. All right, so I'll get us started. What we're going to do is we're going to say u squared is equal to x. That's a reasonable substitution to make because, hey, I'm taking the square root of x. So apparently we're assuming x is what? We keep it real in here. It's positive, right? Non-negative at least. So u squared equals to x is not nuts, right? Now, once I say this, what's this make square root of x equal to? U, right? And we also have 2u du is equal to dx. So with that substitution, what do we got? We've got 2u du divided by 1 plus u. Oh man, that's an integral of a rational function in u. Now we're lost. We don't know what to, no, we do know what to do, right? It's a rational function in u. We can do those. What do you guys want me to do? Long division or my trick? I'm going to do my trick. When you have equal powers in the numerator and the denominator, here's a convenient trick to know about. I do 2 times 1 plus u. Then, to be fair, I have to do what? What do I have here? I've got 2u, right? I just added 2, didn't I? So to be fair, I have to subtract it. And so that simplifies to what? 2 du minus 2 over 1 plus u du. You're like, what? Fine. If you insist, we can do the long division. So we're dividing by 1 plus u. And so I get what? I get 2. So my remainder is minus 2. So therefore, 2u over 1 plus u is equal to 2 minus 2 over 1 plus u, which of course is what I just derived right over here. Sorry about the du. Typo. I derived over here by adding 0. So whatever method floats your boat, it's fine with me. I don't care. But some way or another, you have to know how to do this algebra because that's what we need to do in order to be able to make the integration, right? So then we integrate. What do we get? Two u, yeah. Minus what? 2 natural log absolute value of 1 plus u plus a constant, right? Which is what? 2 square root of x minus twice the natural log of 1 plus the square root of x. I can safely delete the absolute value bars because why? Right, exactly. This next example will give us more experience with long division and partial fractions, so it's a good one. Let's give you another idea about the kind of games we can play here. If I have the integral of dx over, all right, the cube root of x plus the square root of x. What kind of rationalizing substitution am I going to want to make here? What's that? Well, here I made a u squared equals to x substitution to get rid of the square root, right? So the square is the natural enemy of the square root. If I just had a cube, like u cubed equal to x would be a good thing, right? But I got to get rid of a square and a cube at the same time. Exactly. U to the 6th equal to x is the way to go here. Now if I do that, then let's see here. X to the 1/3 is really what? U to the 6/3, which is otherwise known as u squared. X to the 1/2 is what? U to the 6/2, which is u cubed. How about dx? What's dx? 6 u to the 5th du, right? So here's my rationalizing substitution thought bubble. Let's put it into practice over here. What do we get? Six u to the 5th du divided by what? Yeah, u squared plus u cubed, right? Lo and behold, we have a rational function in u. We're off to the races because we can integrate that by partial fractions. Yes, sir? Ah, okay. Glad to help. I think we can do some algebra before we do anything terribly sophisticated here. We can reduce the power, right? Divide the top and the bottom by what? U squared, right? What do we get? We get 6u cubed du divided by what? 1 plus u. Or u plus 1 if you wrote the cube term first. Yeah. So then what? Well, that's a cube over a linear term, right? That's quite improper. You wouldn't let this into the party or whatever, I don't know. But okay, so we do what? This one, my adding 0 trick, not so successful for. You'd need more ingenuity to do that. We'll just pay the price and do the long division. Not a high price to pay. What do we got? We're dividing 1 plus u into 6u cubed, right? So to get 6u cubed from this, maybe I'm going to write u plus 1. It's easier to think about. Okay, u plus 1. So first of all, I get 6u squared, right? That gives me 6u squared plus 6. I subtract that, right? That gives me what? Oh, I'm sorry, 6u squared. 6u, I'm an idiot. Yeah, 6u cubed plus what? 6u squared, right? Duh. Sorry. So then that minus 6u squared is my first remainder. Of course, we're not done. How can we get this from that? Minus 6u. So that gives me minus 6u squared minus 6u. The next remainder is 6u. How do I get 6u from this? Plus 6, right? And so that gives me 6u plus 6. So apparently minus 6 is my remainder. So what I have here is I have the integral of 6u squared minus 6u plus 6 minus 6. A lot of 6's in this problem, plus 1 over u du. May I advocate we factor out a 6? I think we can all see that step. 6. All right, I'm going to pull the 6 out. This is going to be what? 1/3 u cubed minus 1/2 u squared plus u minus the natural log of 1 plus u, which I don't need the absolute value signs for because, you know, it's pretty clear 1 plus u is positive here. We're not done though. We need to write our answer in terms of x. So how do we get back to the world of the x? Let's see here. I'll multiply the 6 back through. Let's see, we got 6/3 is what? So I've got 2 square root of x minus 3 cube root of x plus 6 times x to the 1/6 power, the 6th root of x. I guess I could rewrite that as, just to be in concert with my other notation, the 6th root of x, right? 6 times the 6th root of x. And then minus the natural log of 1 plus the 6th root of x. And I think I forgot my 6 on that last term. There we go. Sometimes it's fun to think back to how we started anti-differentiation, right? Somebody wrote they introduced the concept to you, they wrote something on the board, and they probably asked you to guess the integral, right? Like, what function can you differentiate and get back to the integrand? So when you're asked that kind of question for something like, I don't know, x, you're like, oh, okay, so 1/2 x squared. It's not hard to see that I can differentiate this and get back to there, right? We can all guess that. I like at this kind of point in our experience, our calculus experience, to point out to you, yes, this is educated guessing, right? But could you guess that? Well, here's the function that if you differentiate, you get back to that. No, I don't think I can't guess it. And yet, these integration techniques give us ways to find these things. It's kind of funny. Any questions about this? Let's see how much time I have left. When do we go? Let's see, it's 9. We go till 9:30. Is that right? Okay. There's also an e to the x kind of substitution. I'll probably do that tomorrow with you guys. I want to talk about what's called the Weierstrass substitution in the time that's left. I guess I could put it over here. I don't know. So this Weierstrass substitution goes back to, well, Weierstrass. Weierstrass was an important 19th century mathematician. A lot of influence on our modern ideas about analysis. But he also is known for this particular trick, technique, whatever you want to call it. Although, honestly, I would not be terribly surprised to find out, like, maybe Euler did it or something. It's, generically speaking, a safe thing to say, oh, Euler probably did it. Euler did, like, everything. Our notation for, like, exponential, I think maybe sine, cosine, like a lot of our modern exponential modern notation is really due to Euler. But here's the idea. We let u equal to the tangent of x over 2. A lot of other books use t equals tangent of x over 2 for this substitution. I'm going to stick with the book, though. U equals tangent of x over 2. This substitution will allow us to convert rational function of sine and cosine to a rational function in u in the following way. So if this is u, I can draw a triangle for it, right? And the triangle would have this angle, x over 2. And let's see here, what we'd have u maybe here, we'd have 1 here. What would the hypotenuse then be? Yeah, 1 squared, so 1 plus u squared, right? So in view of that, what would the, what would the sine, what's sine of x over 2? What's cosine of x over 2? Yeah, you said sine is what? You said u over 1 square root of 1 plus u squared, right? And cosine was what? 1 over square root of 1 plus u squared, right? How can we get sine and cosine x from, like, sine of half x and cosine of half x?